So this is the last lecture of the semester. We're going to have one more meeting on Thursday, but that's just going to be final project presentations. The project isn't actually due until next week, Thursday, so I don't expect presentations to give a complete picture of your projects. You should just talk about the background, the problem you're studying, or what papers are you reading for your survey, what are you implementing, what the goals are, and then give a little bit of background on the literature in the area. So talk a little bit about what's been done in prior work and what you hope to do. So that's what I'm hoping to see Thursday. And I sent an email with instructions for the final presentations. Maybe I'll resend it. So each group has 8 minutes. If your group has more than one person, you can split time however you'd like amongst yourselves. You can split work however you'd like. One person can make slides and the other person can talk. You can both talk 50-50. You can do whatever. I don't care. But you only have 8 minutes, and I'm going to time things very precisely. OK, so today, the final thing that we're going to talk about is massively parallel computation. We're just going to spend this one lecture on that. This is where we have a kind of a distributed environment. There are lots of, think Google, right? You have like 1 million machines. You have some computational problem you want to solve. How do you make use of having these many, many machines to do things efficiently? So work on massively parallel computation, as far as I could see, well, from a survey I found, started as early as 76, maybe even earlier. If you want to see more, there's a survey by Epstein and Galil. That's in 88. And there, the model was PRAM. And the idea behind PRAM is, you ignore communication as well as synchronization. Okay, so you assume that there's a shared memory, and you just ignore any synchronization issues. All processors can read and write to this shared memory, and try to understand time versus number of processors. So when I say ignore communication, I mean there's a shared memory amongst all processors. Okay, so a lot of the results there are of the form, if you give me n-cubed machines for a problem of size n, I can do whatever. I can multiply two n by n matrices in polylog n time. Okay, so this is the kind of thing you see there. Given poly n processors for some poly, I can do things very, very quickly in polylog time. Unfortunately, this ignoring communication and synchronization and this shared memory are unfortunately unrealistic. And I would say kind of somewhere, I don't know exactly when, but somewhere in the late 80s, maybe early 90s, PRAM sort of stopped being studied so much. I think in big part because of the fact that you can't just ignore communication. That's actually one of the biggest issues when you're dealing with massively parallel computation. After PRAM, there was the bulk synchronous parallel model. This is due to Valiant, right? Les Valiant here at Harvard. And in this model, you explicitly worry about the things that you should also be worrying about, like communication between machines and synchronization. And the BSP model is actually something that still exists today. So this is 1990. This is a 0. But today you look at systems like Apache, and like Google's Pregel. For graph processing. So these are based on Valiant's original BSP model back in 1990. Today we're going to talk about a model that's simpler to introduce. It has less parameters. Today we're going to talk about Mapreduce. Okay, and that was introduced by Dean and Gemawat. Okay, and again, this is a model for, well, this is a system that was built that's actually used at Google right now to deal with massively parallel jobs. And you also have, Hadoop is an open source version. And these two systems are used by, Google, Facebook, Amazon, you name it. There are tons of places where this thing is used, so it's widely prevalent. And today I'm going to talk a little bit about, kind of a theoretical model for working with these systems and trying to develop efficient algorithms within this model. Okay. I guess I should, just since I put Hadoop, I should also at least put Yahoo. So. Okay, so in this model, I imagine that data items are each key value pairs, and I'm going to consistently use this notation throughout lecture. So a data item is always angle bracket, colon, angle bracket with key and value separated like this. And we have to compute something. Okay. Computation is broken up into rounds. Okay, and what does a round look like? So a round consists of 3 phases in order. There's map. So in the map phase, each item is processed by some map function. Okay, so a map function takes as input a key value pair. And what it's allowed to do is it's allowed to spit out a set of key value pairs. Okay? And it emits or spits out a set of new key value pairs. Okay, they can have the same key as the original item. They can have different keys. They don't even have to have the same key as each other. They can have arbitrary values. Okay, so the mapper is some arbitrary computation. Okay. Then there's 2. The shuffle phase. Okay, and what this does is, this is oblivious to the programmer. This just happens internally in Mapreduce. All keys emitted in, okay, all items, let's say, all items emitted in the map phase are grouped by key. Okay, and items with the same key sent to same reducer. Okay, what's a reducer? A reducer is a machine that reduces in the final phase. So this is the third phase is reduce. So a machine, a reducer, which is a machine, it receives a key k as well as a bunch of values v1, v2, vr, and emits new set of keys, new set of items. Okay. Technically, in the system, the items that it spits out should have the same key as the items that as the list that came into it. But in one extra round, you can just use the mapper to change the keys. So let's just pretend that it can admit different keys as well. Okay, questions? Any questions about? Okay. Okay, so what kinds of goals do we have now within this model? And we're going to look at certain problems, so you'll see exactly how things work in this model. Okay, so one goal is we want to have a few number of rounds. Okay. Another one is want to use much less than n memory per reducer. Okay. So you could imagine one trivial thing I could do is for each item in the input, I just map it to a let's say I'll map. So the trivial thing is to map all key value pairs to to something like this, right? If I map all key value pairs in the input to the key $ with the value k comma v, then by the semantics of shuffle, all items that have the same key get sent to the same reducer, which means that since every item has $ as its key, they all get sent to the same reducer, which means that the reducer is then just has all the data and is doing some computation on it. Okay, so this is like not taking advantage of parallelization at all. This is just doing all the computation on a single machine. Okay, so. But I don't want to allow this. I want to make sure that my algorithms are using much less than n memory per reducer. Okay. And other things that we'll try and shoot for is, so another, right, so I also want, let's say, want much less than n squared, let's say, total memory used. Okay. So another thing I could do is, send, or related thing I could do is send there are n data items. I'll send all n data items to n machines, and then I'll try to have each machine do something locally with one item or something. Okay. So I want to avoid using n squared total memory. In fact, ideally, I want to use nearly linear total memory across all machines when you sum up the memory used by all machines. But as a first pass, we're going to shoot for something like this. And when I say much less than, I'm happy to, as a first pass, I'm happy to have n to the 0.9 memory per reducer. Okay, but I don't want to use, n or even n over polylog n. Good. Okay, so let's see some algorithms in this model. Oh, I guess there's another goal, which is maybe small total work. Where by total work, I mean number of machines times, say max work per machine. Or what might be, more interesting is small, parallel work. Okay, which means what's the maximum time spent by any machine? Times the number of rounds, let's say. Right, so there are always, the classic problems you can look at in a parallel, well, when you're studying algorithm design and you're looking at a new model, there are certain go-to problems you always go and look at. So one example is like sorting. Okay, so one question is, how do you sort efficiently in this model? Okay. And the algorithm I'm going to tell you about is called Terasort, okay, which is in the paper by, well, it's like a white paper. Okay. Actually, the Terasort implementation described there was designed specifically to sort integers of some bounded number of bits, let's say 32-bit integers or 64-bit integers. And there are some extra tricks that are used in that implementation to get speed up, using that fact. So I'll maybe say a sentence about it at the end, but I'm going to give a simplified version of Terasort, which just sorts arbitrary comparable elements. Okay, so I'm not gonna say that the keys being sorted are bounded integers. So I'm gonna leave out one of the tricks in the actual Terasort. And so the basic idea behind Terasort is as follows. So let's say input elements are of the form, let's say, AI, okay, where we have this unsorted array A1n. Okay, and the basic idea is, say we want to use P machines, P machines, okay, in parallel. What we'd like to do is somehow get the smallest, so divide the elements, the n elements, into P groups of equal size, like the smallest n over P elements, the next smallest n over P elements, etc. And then what we'd like to do is we'd like to send the smallest n over P elements to machine 1, the second smallest machine elements to machine 2, etc. Each one sorts their machines locally and then concatenate all the sorted things at the end. Okay, that's what we're trying to do. So the issue with that is we don't know who the smallest n over P elements are, who the next n over P elements are, etc. Okay, so the way we're going to get around that is by figuring that out approximately, and we're going to do a 2-round algorithm. So the basic idea is to attempt to find smallest P elements, smallest n over P elements, next n over P, etc. Send jth batch of n over P elements to machine J to be sorted. Okay. So how are we going to figure out roughly the thresholds for who's the smallest n over p, next n over p, et cetera? We're going to sample. Okay. So let me just write the pseudocode here. So this is going to be a 2-round algorithm. So let's say round 1 looks as follows. So map, let's say I'm defining now the map function, which takes as input an I and an AI. Okay. And what I'm going to do is I'm going to emit I mod p AI. And also, so here I'm going to set t to be something like log p over epsilon squared. We'll see where this comes from in a second. The other thing we're going to do is, with probability t over n, so we're going to flip a coin. With probability t over n, for j equals 0 up to p, we're going to emit j AI. Okay. So what's happening here? In our first round, after we do the map, we evenly partition the n elements into p groups of size n over p and send them. These are not sorted, remember. These are just, just take the first p elements in the, well, because I did mod, it's not the first p, but just take some group of n over p elements in the array, send them to machine 0, then send the next n over p to machine 1, et cetera. They're not sorted. And then I'm also sampling elements from the input array. The total number of, in expectation, the total number of input elements that I'm sampling is t, which is something like log p over epsilon squared. We'll set epsilon in a second. And if an item decides to be sampled, then what I'm going to do is I'm going to send that item to every single reducer. Okay? So for each reducer j, I guess it goes up to p minus 1. For each reducer j, I send this item to that reducer, okay? Just the value. Okay? Good. So that's map in round 1. What is reduce? So reduce gets as input, it gets as input some j, which is a number between 0 and p minus 1. And it also gets a list of elements x. Some of the elements, and let me also do this. Let me say this is actually I comma AI. Okay. So some of the elements from x are these types of elements. They're pairs I comma AI. Okay. And then some of the elements in x are just single numbers, which are the sampled elements. So let's partition them. So say B are the I AI, and S is the set of sampled elements. Okay. So reduce is doing this local computation on X. And then what I'm going to do is I'm going to set S to be the sorted of S. Okay. So what I hope happens, let me write that right here. So what I hope is pretend this were the array as if it were sorted. Okay, and I'm sampling T elements, capital T elements. What should happen, kind of an expectation, is that this guy, the first guy is like a 1 over t plus 1 fraction of the way along. The next guy is a 2 over t plus 1 fraction of the way along, et cetera. Okay, and this is a t over t plus 1 fraction of the way along. Okay, and these are the guys. What I hope happens is that these are the guys who got sampled. in the sorted order. Okay? And then what I'm going to say is kind of look down to the level where this is 1 over p 1 over p fraction, or let's say, so there are these t elements, and I sort them, capital T elements in expectation. Let's say capital T elements, and I sort them. After I sort them, look at the guy who's at index capital T over p. So he's a 1 over p fraction of the way along. Kind of what I hope happened is that the guy who's a 1 over p fraction of the way along in the sample is also a 1 over p fraction of the way along in the actual sorted array. But there's some randomness. He's not going to be exactly 1 over p fraction of the way along, but he's going to be something close to it. And what I'm going to do is I'm going to use him as the pivot to decide who should have gotten sent to machine 0. So everybody less than him should have gotten sent to machine 0. And then what I'm going to do is, okay, look at the guy at index 2t over p, right? He should have been a 2 over p fraction of the way along in the original array. So everyone between him and the first guy is going to get sent to machine 1. And I'm going to use these as surrogates for the actual people who are at index n over p, 2n over p, et cetera, in the sorted array. Okay? So now what I'm going to do is, for each I comma x in B, find some r in 0 p minus 1 that x should map to in relation to s. And what I'm going to do is I'm going to emit R together with IX. Okay. So kind of every reducer has, the reducers have two jobs. Okay. One job of the reducer is to find these approximate quantiles in the sorted array. And then the next job of the reducer is to take the n over p elements that map to it and see compare them to those approximate quantiles and see roughly where in the sorted order they are. Okay. And then map them to the corresponding reducer for round 2. Right, so now there's round 2. The input to round 2 is the output of the reducers from round 1. So it's all these r's, comma, ix's. So what's the map function? It's just the identity function. Okay, so map doesn't do anything in round 2. Map gets as input an r, comma, ix, and it just spits it back out. And reduce, so reduce gets as input some j together with a set of items. And then what we're going to do is just sort B by second element. And then kind of write the output to j dot out or something. Okay. And then to get the actual sorted order at the very end, you just concatenate 0 dot out, 1 dot out, 2 dot out up to p minus 1 dot out. Does that make sense? Okay, so let's analyze this quickly. So what's the total memory required per machine? So let's say analysis now. Okay, so first of all, I want to balance, I have to choose epsilon. I haven't told you what epsilon is. Okay. So how am I going to do that? Well, I guess there are a couple things there's one thing I want to balance, which is I know that in the reduce step, each reducer is getting the set B of items from the array that map to it. That set B has size n over p. So I'm getting a set of size n over p, which is like sort of evenly spreading the work, right? There are n elements to be sorted, so that's great. And in addition to those n over p elements that I'm getting, I'm also getting log p over epsilon squared elements, right? So that's one thing I want to be balanced. So the log p over epsilon squared should be like at most n over p for this to make some sense. The other thing that I want balanced is, OK, so ideally what I want to happen is, so there are these n over p elements that map to reduce. And then reduce takes its set of n over p elements and figures out which quantiles they're in, roughly, right? Between which two quantiles they're in. And then there's a second reduce phase that sorts all the items that it thinks are in its quantile, right? So Turnoff Bound says a Turnoff Bound and a Union Bound. So let's just focus on one reducer. Okay. Now, if we just sample log 1 over delta over epsilon squared elements, forget about Mapreduce for a second. Just take an array and sample log 1 over delta epsilon squared elements. Okay. And then look at the smallest element, or look at the element that's an alpha fraction of the way along in the sorted order of those sample elements, right? So Turnoff says if you sample log 1 over delta over epsilon squared elements, and let's say let's call this t, and look at alpha tth smallest element in sample, its rank in the actual sorted order of A is going to be something like alpha n plus or minus epsilon n. Let's say there's some constant here, with probability 1 minus delta. Okay, so that's implied by the Turnoff bound. Okay, so maybe I'll just leave that to you as an exercise. Okay. The proof of this is somehow very similar to when we analyzed p-stable, using p-stable distributions for LP norm estimation in data streams. Okay, so the basic idea is kind of you look at people who are more than epsilon n below this guy. Okay, so look at the guy. Look at the guy who's actually at rank alpha n in the sorted order of the array. Okay, now look at everybody whose rank is less than alpha n minus epsilon n. Okay, what an expectation, how many of them survive the sample. Now look at everybody who's alpha n plus epsilon n, who's at most alpha n plus epsilon n in the sorted order. What fraction of them in expectation survive the sample? Okay, and what you can show is that kind of by a Turnoff and Union bound, if you sample this number of people, then you'll have you'll have kind of what you expect with probability 1 minus delta. Okay. So what this tells you is these guys that you're using to estimate the quantiles in your sample are off by this epsilon n. You're off by at most epsilon n in the true rank in the original array A. Okay. So what this implies, so let's say, so continued from that last, well, remember now we set delta we set delta to be something like 1 over p here in RT. So what that means is for each of the p quantiles we care about that we're using to partition our elements to sort, with good probability we're correct on all of them simultaneously. Okay? So what this means is that each reducer in the second round so kind of with high probability, each reducer in the second round gets at most something like n over p plus epsilon n items to sort. In particular, the number of items it gets to sort is between n over p plus epsilon n and n over p minus epsilon n. Okay? And again, I want to balance this. So set epsilon to be something like 1 over p, which implies that capital T was going to be something like log of p over p squared. So going back to the first item there, so we want p squared log p to be at most something like n over p. So the most you can take advantage of here is something like set them to be equal. So now p is something like n to the 1/3 over log n implies with high probability each of the p machines needs to sort at most O of n over p, which is something like O of n to the 2/3 log n items. Okay. So what this algorithm is telling us is if you have roughly n to the 1/3 machines, then each machine only needs n to the 2/3 memory. And all it's doing is sorting those n to the 2/3 items locally. And sorting n to the 2/3 items locally takes roughly n to the 2/3 time, right, up to log n. Right? So we're getting a running time that's scaling sublinearly with n. Right? So our kind of parallel running time is something like n to the 2/3 roughly, up to these logs. Yeah.
Does that imply the number of machines are dependent on the size of n?
Well, I guess what I'm saying is, what this is saying is kind of there's no real advantage to using more than n to the 1/3 machines.
Yeah.
So I mean, the number of machines you have is whatever.
Yeah.
But kind of once the number of machines you have is more than n to the 1/3, this algorithm isn't like getting any better, basically.
But what if you use less than?
Oh, if you're using less, you'll still get some kind of advantage. It's just that kind of the most advantage you get. You keep getting more and more advantage as p grows up until this point. Yeah, with this particular algorithm. Okay. Maybe I'll just say a word about Terasort. So in the algorithm that I've described it, I guess I didn't really mention it. In the first reducer, I said first you sort S. And then for each element of B, you figure out where that element relates to the sorted order in S. How would you do that quickly? Well, you just do binary search, right? So S is now sorted. You have this element, you have this key X. You want to know where X is in relation to this sorted list. You just binary search. And that's the part that Terasort, the actual Terasort, does more efficiently using the fact that the keys are integers. They basically build some tri-data structure to do this more efficiently. So I'm not going to talk about that at all. But I think this is, this gives you a kind of a look at the kinds of things you might want to do in this model. Okay. Okay. say a couple other example problems. So let's look at a graph problem. So I'll show you two graph problems. So min spanning tree. In graphs that are not too sparse. Okay. So in particular, I want to look at the case where m is the number of edges, is n to the 1 plus c for some c bigger than 0. So I have more than just the linear number of edges. And what I want is, I want the memory per machine to be much less than m. Say something that's at least like m to the 1 minus epsilon for some positive constant epsilon. So the algorithm that I'm going to tell you about is due to Karloff, Suri, and Vasilitsky. In Soda 2010. So we're going to, there's going to be some parameter k. Which we'll see in a second. Actually, k is just going to be something like n to the c over 2. And what I'm going to do is I'm going to have a hash function h, which maps vertices into 1 to k. So I'm going to have a random partition of the vertices, v1 up to vk, where vj is what you expect. It's the set of all vertices v such that h of v is equal to j. And then what I want to do is, for each, right now I'm just sort of describing the algorithm in words. Maybe this is the last example where I'll actually, write down pseudocode in the Mapreduce framework I mentioned with map and reduce, so you can see this is actually implementable. Okay. So in the model that I described, so for each. What I'd like to do is for each ij in k squared, okay, so for each pair of vi, vj, I'll do something like let gij is as the induced graph on VI union VJ. Mij, so GI, what's going to happen is Gij is going to be kind of one key. Like I comma j is going to be a possible key coming out of the map phase. Okay. And so there's going to be a reducer that gets all the edges in Gij. And the reducer is going to compute Mij, which is equal to the MST of Gij. And then we're going to set M to be equal to the union over all ij of Mij. One last reducer outputs the MST of M. Okay. So that's the algorithm. Is it clearer that that this can be implemented in Mapreduce and like how many rounds you need, right? So the basic idea, maybe I'll just start writing this. So in Mapreduce, so there's round one. Let's say the inputs to map are just edges, u comma v, and the key doesn't matter. Let's say the value doesn't matter. The value is null, let's say. And what we're going to do is just emit so the key is going to be hash of u comma hash of v. Right? So in particular, these GIJs partition the edges. Right? So the key is going to be h of u comma h of v, and then the value is going to be uv. And then there's going to be a reducer which takes as input some ij pair, telling me which induced graph I'm looking at. Question? Oh, edges inside VI appear in multiple places, you mean? That is, oh, I see what you mean. Yeah, so, yeah, but I guess it also means that I need to change how the map works, right? Because if U and V actually lies within the same partition, then I need to I need to also emit to all other places where that edge appears. Do you see what I mean? Yeah. So what I should say is there's an if statement of h of u is equal to h of v, which is equal to I. Then for each j, I guess there's also a weight here, which I've been ignoring. So the edge also has a weight. Okay, so for each j going from 1 up to k, I'll also emit ij uv. Yeah. So yeah, that's right. They don't partition the edges because of that, because of exactly what you said. Then there's reduce, which takes as input which Gij you care about, as well as some sequence of edges. And then it just let E1 up to E. Will there be? Well, it might not be connected. So, and this should not really be an MST. This should really be a minimum spanning forest, because Gij might not actually be a connected graph. But let E1 up to E T be the minimum spanning forest of this Eij. And then for A equals 1 up to T, I'm going to emit Ij together with, or actually what I can say is emit Ij, oh, emit $, let's say, together with the edge and where it came from. Yeah.
Sorry, why do we have to do that extra check for the hashes?
Oh, just because, so as Yarek pointed out, there are some edges whose endpoints both hash to the same partition, right? And you want those edges to, so I mean, my definition of Gij is that it's the induced graph on Vi union Vj. So it's not only the edges that go from Vi to Vj, it's also the edges that are internal to Vi and the edges that are internal to Vj. So in order to have that be true, I needed to make sure that, let's say that both U and V hash to I, right? But then now look at Vi union V1. If I just did this, then that edge that's internal to Vi would not actually survive, would not actually be emitted to I comma 1. Yeah. Does that make sense? Yeah. Okay. So good. So at the end of this, basically the thing that's being emitted here is all the edges of capital M. Capital M is the union of all the Mijs. Right? And they're all getting sent to the same reducer because they all have the same key $. So in round two, the map will just be the identity map. And the reducer will take all these edges as input and then compute the MST of this set of edges. Okay. So let me not write the round 2 reducer on the board. So now the question is, kind of what can we prove about this algorithm? So I'm not going to, the correctness of this algorithm is pretty easy to establish. I'm not going to do that on the board. You can look at the paper if you want. But what about the resource requirements of this algorithm, the memory and the running time, et cetera? In particular, the memory. So analysis of, let's say, the memory. So what I want, the trivial solution, as always, is one machine gets all of the graph and then computes the MST. And I don't want to assume that one of my machines can store the entire graph. Okay? So I want to say that the memory is much smaller than M per machine. So the mem per machine, well, that's at most, how many edges are coming out of I comma j, right? If you look at reducer I comma j in round 1, well, they're k-squared reducers, right? They're k-squared reduced keys. And each one of them is giving you the tree of some subgraph. Okay? So a tree has at most n minus 1 edges. Let's say at most n edges, and there are k squared of them. So the memory per machine is at most, actually, now that I look at this, that's k squared times n seems a little big, actually. So as I did it here, it's k squared times n. Oh yeah, good point. Right. Okay, that's a very good point. So, right. So, the total size of a spanning forest is at most number of vertices minus 1. Let's say at most number of vertices. And as you pointed out, the number of vertices in Gij is roughly, with high probability, it's going to be something like 2n over k. At most big O of n over k. So it's actually something like k squared times big O of n over k. Okay, this right here is, it's going to be at most the size of vi union vj minus 1. And this is big O of kn, which is big O of n to the 1 plus c over 2, which is much less than m, which was n to the 1 plus c. Okay, so I'm using like truly sublinear memory here. So in particular, if the graph is nearly dense, meaning n squared, close to n squared edges, I'm using like n to the 3/2 memory per machine. This is just in round 2. Right, round 2, which gets all of the mij's to then compute m. And then for round 1, the max mem per machine is just equal to the max over all ij of the size of eij. Right. Okay. And what's the expected size of eij? Well, it's the sum over all edges, the probability that the endpoints of E are in Vi union Vj. Okay. But the probability of being in Vi union Vj is something like 2 over k, I guess. Right? The probability that you hash to I is 1 over k. So the probability that you either hash to I or j is 2 over k. So this whole thing here is equal to 2m over k. Okay. So kind of by a turnoff bound followed by a union bound over all ij, you can say that with high probability, none of them are bigger than big O of m over k, which is again n to the 1 plus c over 2. N over k squared? Oh. Yeah, that's a very good. Yeah, so I just did one endpoint. That's a good point. So probably that both. Uh-huh. Oh, actually, so okay, so okay, good. So that's a good point. So the expected size is m over k squared. So I got a little ahead of myself with concentration, I think. Right. So, OK, so concentration isn't just, OK, now let's invoke the turnoff bound. There's a little issue here. In the turnoff bound, you're summing up a bunch of independent random variables, right? And then you want them to be concentrated about their mean. Okay? And you assume in the turnoff bound that these independent random variables you're summing up are bounded, right? And if the bound you have on them isn't great, then the tail bound you get as a result also isn't great. So if you look at how many edges land in the induced graph Gij, well, think about certain vertices. Certain vertices are very high degree. So if you happen to sample them to that partition, then you're actually going to have a lot of edges. So you have you basically have, for turnoff, we have kind of Eij is equal to the sum over vertices v and v of the indicator function of the event that let's write it like this. Well, it's at most this. It's at most this, anyway. H of v is in the set ij times the degree, I guess, of v. I guess you can do better than this. You can do better than just saying this. Okay? And kind of, I guess, what they do in the paper is they say, so Karloff, Suri, Vasilevsky, what they do is partition v according to degrees. And they define something like Vt as the set of all vertices V such that the degree of V, they say, is at most 2 to the t and is at least 2 to the t minus 1. And then now what you do is you kind of do a union bound over all of these VTs, and then you use this bound. And then you say within a particular VT, all the summands are basically bounded by similar things, right? This degree V is basically all the same up to a constant factor. So you're not losing too much by using the turnoff bound now. And at the end of the day, they show that with high probability, the max of Eij is O tilde up to a log n to the 1 plus c over 2. Okay. Yeah, I should, now that you mention it, I mean, this does seem like quite sloppy because just because you sampled him doesn't mean you sampled everyone that he's adjacent to. I'm pretty sure, yeah, I'm fairly sure that's what they're doing. Or maybe I'm mistaken, but anyway, it's something not too crazy, and you get something that's truly sublinear. Sublinear memory per machine. There's one downside. The total memory needed is something like, is roughly k squared times, I guess, n over k. K squared times this thing, n to the 1 plus c over 2. Okay? So kind of what we said was that none of the induced graphs have more than n to the 1 plus c over 2 edges. There are k squared of them. So if you sum up the memory used over all machines, it's something that's like this. K squared is n to the c. So this is equal to something like n to the 1 plus 3c over 2, which is equal to n to the 2 plus, well, what's m? So yeah, so n to the 2 plus c over 2, something like that. which is basically m to the 2 minus epsilon. Right. So the total amount of memory that you're using is less than sending every edge to every machine, but it's not like much less than that, which is not ideal. So there was an algorithm afterward, Latanzi et al. In SPA 2011, which gets O of n to the c machines. So this is like the k squared. O of n to the 1 minus epsilon mem per machine. And something like c over epsilon rounds. Okay, so the total memory here is actually something closer to m as opposed to, in fact, that maybe looks a little bit too good. It looks like it's less than m. Maybe this is plus epsilon. No, it's less. This might be something more than. Sorry, say it again. Yeah, c is the same c that we've been talking about. Yeah, I mean, I think maybe I lost something small here because if you multiply these two things together, it's less than m. So definitely the total memory you're using should be at least m so you can store the graph. So I think this may be c plus something small. There's not a whole lot of time. Let me just say one last thing. So last example problem is triangle counting. Okay. So the number of triangles of G is just defined to be, look at how many U less than V less than W are in the vertex set such that UV, VW, UW are in the edge set. Okay, it's the number of triangles in the graph. Sequentially, if you don't care about parallelism, there's a simple n cubed time algorithm, 3 nested for loops. Right? You just loop over all UVW and then check whether or not all those 3 edges exist. And if so, you increment a counter, you return it. In fact, you can even get m to the 3/2 time. I'll show you that right now. And the Mapreduce algorithm I'm going to show you is basically an implementation of that in Mapreduce. And it's going to use something like, I think, root m. They're going to be root m different reduce keys. And right. And the memory machine per machine is going to be something also very small. Okay. So what's the sequential algorithm that gets this? So let's define a total order on V. We're going to say that U is less than V if the degree U of U is less than the degree of V, or the degrees are equal and U is less than V. So when I say u is less than v, I mean, let's say that we associate with each vertex a number between 1 and n. Okay. So if that ID of u is less than the ID of v. Okay. So the algorithm looks something like this. For v in the vertex set, for u in the vertex set such that u is bigger in this order than v, and then also for w in the vertex set such that w is also bigger than v. Let's say answer is initially 0. Answer, if UVW is a triangle, if all those 3 edges exist, then the answer gets incremented, and then return the answer. Okay? Does that make sense? So, I mean, each triangle, basically, in this code, each triangle is counted exactly once, right? Because this is a total order on the vertices, and well, okay, I guess maybe twice because there's VUW and there's also VWU. But maybe I need to return answer over 2 or something. So why does this algorithm run in time m to the 3 halves? I'm sorry?
Why is it doubled? Isn't it already ordered?
Oh, just because I count like if there's a triangle UVW, I'll count it as v comma u comma w, and also count it as v comma w comma u. Because I'm just saying that u is bigger than v and w is bigger than v. I had v on both sides.
Can you just change that to w is greater than u?
Yeah, I probably could also do that. Yeah. So runtime, pick a threshold t. If the degree of v is bigger than t, is at least t, then we only consider triangles with v containing 2 other greater than t degree vertices, right? So if v has degree at least t, that means u and w also both have degree at least t. But how many vertices are there that have degree at least t? The sum of the degrees is 2m, right? So there are at most 2m over t vertices of degree at least t. So that implies O of m over t cubed such iterations. And then the other case is if degree of v is less than t, right? That implies that at most, well, I guess I should have said such that u is at least v and u is in the neighborhood of v and w is in the neighborhood of v. I only have to loop over neighbors. Right. And then I guess I should just say that. So really, the only thing I really need to check is that UW is an edge. Almost t squared time. the total amount of time spent in these iterations is at most the sum of v such that degree v is at most t of degree v squared, which is at most t times the sum of the degrees, which is at most 2mt. So you can balance this. So the time is at most O of m cubed over t cubed plus mt, which is equal to O of m to the 3/2 for t equals root m. Okay. And now how do I use this to implement a Mapreduce algorithm? So there's round one, where map gets as input edges. And it just says if u is actually bigger than v in this order, then I'll emit vu. And then my reduce gets as input v together with some set s, where here s is a subset of the neighborhood. It's the people in the neighborhood who are bigger in the partial order. And then what it says is for uw and s, emit v uw if uw is an edge. And then there's round two. Map gets as input. So there are two cases for the input map gets. So I'm going to imagine that the inputs that were in round one will also appear in round two. So I could achieve that by just like re-emitting them, and reducers also spit them back out. Plus, I'm also getting these outputs. So if the input is of the form VUW, then emit UWV. Otherwise, if the input looks like an edge like that, then emit UW $. And then finally, let me just say the reducer in the last second. If $sign is in S, then for each V and S, such that V is not the $sign, I'm going to emit V1. Okay, so at the end of the day, what I'm emitting are basically all the items. So for each time V appears in a triangle, I do an emission. Okay, so at the end of round 2, all the emissions correspond to triangles. Or I guess maybe there's this double counting because of that same issue, and then you have to divide by 2. And then there's a final aggregation stage, which just has to basically sum up how many things there are. So I think that's, yeah, unfortunately I'm out of time. I don't know, do you have any questions, last-second questions about anything? Okay. Oh, are those P-sets? Okay, so I guess we'll hand them back maybe Thursday. Okay, great.